All right. Well, Larkin, thank you for joining us today to present. And Jun, thanks for coming as backup for this presentation. We're excited about it. This is sort of a left field topic for us, such as anything can be, although to be fair, almost everything is kind of a left field topic in terms of what sorts of events we hold, but I'm super excited about it. I've always been kind of fascinated by anything relating to games, and not game theory, but rather the theory of games. And there seems to be some degree of connection here, so I'm looking forward to understanding that better. And we have an extremely diverse, although small, crowd today. So hopefully the Q&A will reflect that fact, which I think is pretty cool. So with that, Larkin, take it away. The floor is yours, and thanks again for joining us.
Okay, thanks so much, Max. Yeah, my name is Larkin Liu, and I'll be presenting the topic you see in front of you, an extensible and modular design and implementation of Monte Carlo tree search for JVM. I know I'm reading off the slide, but it is what it is. Sorry, the name is what it is. And it's essentially a software package that runs Monte Carlo tree search. And I'm gonna talk about the way that was designed and why it was clever, or why it was innovative. So without further ado, yeah, Max, thanks for having us on this talk series, and I hope you enjoy the presentation. The structure will be, we'll just talk about our biographies real quickly. I'll then go over some basic mathematical theory. I will then talk about solutions via the mathematical approach. Then I'll talk about the Monte Carlo approach, and then finally, the last phase, we'll talk about the design of the software itself. But I think from 1 to 4 will be a lot faster, and 5 will be the main core of the topic, because our presentation is essentially a software package. So just quickly go through our biographies real quickly. Myself, I'm a Chinese Canadian research scientist. I studied first at the University of Toronto, where I majored in industrial engineering, and I worked in industry as a data scientist for several years, and now I'm a doctoral student in Germany, here at the Technical University of Munich, where I conduct research in supply chain optimization. Jun is also Chinese Canadian, but he's a real software engineer in this mix. He did his bachelor's in engineering science at the University of Toronto. Then he worked at Microsoft extensively for 5 or 6 years or so, and now he's a master's student at Carnegie Mellon University. So let's jump right into the I guess the math part of things. And what are we ultimately trying to do with Monte Carlo tree search here? The Monte Carlo tree search is essentially solving what's known as a Markov decision process, where it's a decision process where an agent in a world, in an unexplored world, can take actions in the action space. Each action will return a reward, and also potentially transition the agent or a robot into a new state. We focus in the world of discrete MDPs, where you take an action and it'll move you to another state, and of course you'll obtain a state. And so the key takeaway in this, I don't want people to be too sidetracked by all the fancy notation, but the key takeaway is that the agent, when you take an action in a discrete state action space, you obtain a reward as denoted by R, and you also transition to another state with some probability function by P, and that state also has a value, and you can see the value is recursive. And so solutions to these problems can be very intractable due to this recursive nature, where it has to compute the future and then recursively compute for the future again and again. And there are clever ways in dynamic programming to solve this problem, notably value and policy iteration. But even with these clever methods in dynamic programming, MDPs become wildly intractable as the state action space increases. And so this is an area that I currently research in. And for any researcher out there, I think when you investigate a problem, first you might want to start building some of the tooling of how you want to attack this problem. And so this is why me and Jun had the idea of creating MC Tree Search for J, which is a Monte Carlo tree search solver for MDPs in the JVM. And we'll go over why we built this later, but this is more of just a mathematical theory. And so one of the key takeaways is we have a Q function essentially, which is the reward and the probability of transitioning into the next state given the action taken and the value of that next state recursively, plus a discount factor. So this is basically what we're trying to always maximize with our agent here when it's walking through a system. And so what are the key challenges for MDPs in the real world? A lot of times there are nice solutions from the analytical side of things, but a lot of times like transition probabilities are unknown. So we don't know with what probability are we going to transition to another state when we take a certain action. We can keep playing the simulation again and again, but we may not be able to actually mathematically define the system. This is a key challenge. There are a lot of imperfect conditions, unobservability, which then we jump into the world of PO-MDPs or partially observable MDPs. And then there's also high dimensionality of state action space, which I just mentioned before, making a lot of these things very difficult to compute. And so traditionally, as I mentioned earlier, the solutions are coming from dynamic programming, coming from stochastic programming, and mixed integer programming or convex optimization. These are more of the exact solutions or approximate solutions that are inspired by exact solutions that are state-of-the-art, but they're quite complex compared to Monte Carlo tree search. And as you can see, some of them already do use Monte Carlo methods in addition to dynamic programming. But we will not focus on this because we'll be focusing on the Monte Carlo tree search side of things and how we would solve MDPs using that technology. So this is just a little bit of mathematical theory. The multi-arm bandit problem. So what is, I'm not sure if anyone's familiar with multi-arm bandits. Maybe you are, maybe you aren't, but what is it connected to? How is it connected to MDPs? Well, basically, the multi-arm bandit is just a it's just the MDP which doesn't transition states, right? Like we want to know how much reward we're getting with each action we're taking, but the state is the same. And so basically, sorry, MCTS is ultimately an extension of a solution to a multi-arm bandit strategy. And so in multi-arm bandits, we are again trying to, well, not again, but we're trying to minimize what's known as the regret, which is the value of an optimal policy, minus the value of the current policy. And the value is defined by the reward that we obtain given the action that we take, with a probability of that action under the policy. So there's a probability that we take an action under the policy, and we sum it all up, the reward for each of the actions that we take, and that's the value of the policy. And so the regret is the difference between that and the optimal policy. And that's.
I'm sorry, can I interrupt and ask a question real quick?
Go ahead.
So do you think you can give a little bit of a high level of how the multi-arm bandit fits with the Monte Carlo for MPT? Because it feels like Monte Carlo is like, I have all these choices and it's like, multi-arm bandit, it's like, which one choice do I make that will help me the most? And the MPT seems like something that's, Monte Carlo's like, you have to recurse in a lot of ways to find the solution. Like,
yeah, exactly.
Am I jumping ahead, or did I miss something about how these are connected?
So there's, if I'm not mistaken, there's not much recursion going on, and there's no recursion going on in the formulation for multi-arm bandit. The reason why it's in this slide set is because I wanted to demonstrate that actually, so one of the mechanisms in Monte Carlo tree search is an evolution of multi-arm bandits. And so that's why it's in there. But as you see, the key difference between multi-arm bandit and an MDP is that there's no transition of states. So we obtain a reward with the action under a policy, but we don't change the state of the agent. We don't go somewhere else as a result of taking a step or something, as a result of selecting something or taking a step or observing something. We don't change the world that we're in, or the state of the world that we're in. We just kind of stay in the same position. And simply in a multi-arm bandit, we're just trying to minimize, because we don't know what reward we get with each action that we take. So we could have maybe 3 actions, but we don't know, maybe 3 restaurants, for example, in the neighborhood, each yields a different reward, but you have to keep trying them to know. So this is basically what a multi-arm bandit is. And of course, if we know exactly what restaurant you want to go to yield you the best reward, then you keep going there all the time, but you have to keep trying them to know. But of course, when you keep trying a restaurant, potentially, or in principle, it does not change the state of the world that you're in. You just kind of stay the same. And so you're just trying to find the best arm to play, so to speak.
Right. So the traditional metaphor of the multi-arm bandit is literally the slot machines, right? So you're saying you're now in a problem where when you pull the arm on one of the slot machines, you might go through a trap door to a new casino. And so it's like a completely different kind of problem, because you literally could switch casinos when you do it, which means that you don't have this possibility of like retrying that same bandit in order to get a better sense of its probability distribution or something.
I think the trapdoor, the example you kind of posed, the thought experiment, so to speak, that none of this actually happens, but this would be the MDP, where every time you play an action, you have the potential of moving to a new world where the probability distributions are now different. But in a multi-arm bandit, in principle, by design, you're not changing the world you're in. You're simply trying to find what's most rewarding for you to take in a world that's kind of unknown. So obviously, this type of thing I've worked with before. For example, in ad tech, you want to show certain advertisements that yield different click-through rates. Well, assuming the customers don't change, or the people don't change, your audience doesn't change, which advertisement is the best. We don't want to display equally to everybody. We want to maybe focus fire on the treatment that will get you the highest reward. And so these type of things help us find it faster instead of taking a long time for you to discover. And so this is not the focus of this presentation, but one way that you do multi-arm bandit is through a well-known strategy called UCB1. And basically, we would play the arm where it is the reward, the mean reward that you got before. So maybe you played it a couple of times, you already know what reward you get. The mean of that is your estimate, because there is some stochasticity in there, plus some adjustment factor. It will be adjusted by it will be punished, so to speak, more if by the NA, number of times you already played that arm, and then normalized by the number of times the game has been played in total. So basically, if you tried it too many times, it's going to penalize you a bit more. And then, but it's normalized by the total amount of times you play the game. And so this additional factor allows people to keep to not be greedy and just, let's say, play the reward that got you the best reward last time. Well, maybe you didn't discover something. So this is the adjustment factor. And this is a well-known formula for the multi-arm bandit. And so now we jump into the MDP world, where we do change states. Well, as you can see in the graph ahead of you, as you can see, the agent will move from state to state down a tree. So now, how do we normalize? Well, of course, we want to play we want to move the agent into a state where it's most rewarding, but at the same time, we want to also explore, right? So now this is called the UCT strategy, which is based off of the UCB1 strategy from multi-arm bandit, where each time the agent jumps into a new state down the decision tree, it is trying to look for the state that it's visited before will yield the best expected reward, plus some adjustment factor from UCB1, which is normalized by the total number of times that node has been visited, divided by the number of times the next node, the proposed node, has been visited. The shorthand is the apostrophe. So this is how the original Monte Carlo tree search works. The agent goes down the tree, and then it's gonna greedily select the next state, potentially that has visited before, that yields the best reward. At the same time, it's normalized by a punishment factor if you visit that place too many times. So it encourages exploration. And so just a quick some citations. Certain papers in the past have demonstrated that Monte Carlo tree search. So in Chang 2005, they demonstrated that MCTS is actually just an adaptation of the multi-arm bandit for MDPs. And Bertelsmann in 2014 showed that when comparing Monte Carlo tree search to mathematical programming, like dynamic programming, for example, the performances are similar and they use, but they have interesting results, so to speak. The MCTS, is favorable in certain scenarios. So I'll just sum it up. What are the challenges of MCTS? Well, oftentimes for MCTS, we tend to fall into local minimas or maximas, and it's hard to escape them. There's no guarantees on the value, on the convergence of any the value function in any imperfect scenarios. So yeah, that kind of draws from the first point. There's no guarantee that you're going to get an optimal solution. There's a lot of guesswork involved with determining, which heuristics that you should use that are going to be the good ones. It's just a proposal. I think this is going to be like this, and let's try it out. And it's experiment and trial and error. A lot of trial and error involved. So a lot of the mathematicians don't like this. But the advantages are, as I mentioned earlier, it doesn't require any knowledge of. It doesn't require you to mathematically explain the system. Because as long as you have some sort of programmatic simulation, then it's fine. It will demonstrate this. It does not scale to the size of the state action space, right? You can set the number of simulation parameter, the number of iterations down a tree. It does not need to compute for everything. It could just compute. It could just solve for a subsample, and if that could be an approximate solution to an optimal solution. And again, it can easily be mixed up with different other solution methods. And we've seen this before in other research areas where dynamic programming has been married with Monte Carlo tree search to yield effective results. And so now we talked about Monte Carlo tree search, the key ideas. Actually, I need to explain maybe real quickly. So how does Monte Carlo tree search work? We have an agent looking through, basically searching through a system. And you can imagine a decision tree here. Each action it takes, it goes to another state. And so the nodes here are the states that have already been visited. So at some point in the past, in the selection phase, these nodes here have already been visited. And so now that all the selection phase does is propose where to go. So using, this is driven by the equation number 9 here. It proposes where the agent should explore. And once it hits a certain point, it's going to propose to, now we've hit a phase we want to expand to a new area we haven't searched before. Once expanding to a new area, then we have to play a variety of random games, random traversals further down the tree to know what the result of this state would be, what the reward of this state would ultimately be. And then back propagate the reward up to all the way to the root nodes. So each of the values are dependent on the next nodes, and all of this is back propagated up, and all the values in this stream get updated. So that's how the MCTS works in a very high level. And so we want to design a software that we can run MCTS for both, and it was dual intent. So one was to create a basis for research and development, and the other one was to make it a very industry standard piece of software. And so the background is that MCTS in general, although we know it's really well used in research, especially for like a DeepMind and a lot of AI driving simulations, etc. These things, Monte Carlo methods are, such as Monte Carlo tree search, are well known to be used, but there's a lack of general implementation of this in the open source world, that is. I'm sure, from the closed source world, there's a lot of good implementations on the industry side, but as far as open source is concerned, there isn't a lot of them. There definitely isn't a lot of them in the JVM, as it's already lacking machine learning implementations in general. And research in general also lacks a lot of reproducibility. And the aim was to develop a software that's very easy to reproduce, which we'll demonstrate later. And it's very applicable to a variety of research problems. And so why, so one of the quick questions would be, why did you go with JVM and Kotlin? Well, JVM actually, despite its lack of support on the research side, it's actually it's a very well used industry language, especially for web frameworks, desktops, Android, etc. And Java is very popular actually, and has it has an extensive support base and knowledge base, which we can take advantage of. And speaking of Android, actually, a lot of mobile games are designed with Android, obviously, which use JVM. And I would assume these games sometimes are term-based, and they do require some sort of Monte Carlo tree search. And it would be nice to see this type of stuff being used for these type of mobile games. And Kotlin, well, Kotlin is a newer language. It runs on a JVM. It's got a very nice, succinct and expressive syntax, got a lot of powerful primitives, and it's very modern. So we picked this as to develop the MCTS framework on. This is a key slide. Now, when creating this package, what were the key things that we had in mind? Well, one was extensibility. So as we talked about earlier, there's clearly various 4 key mechanisms in MCTS, and then how we choose to do the search. A lot of these methods can be reused, and so we wanted to make sure that the package was extensible and reusable. As by extension, also modular, in the sense that if you wanted to change something with how MCTS runs, it's not going to be that hard to do. You can definitely rewrite a certain component and plug it back in, and you shouldn't require a complete rewrite. And then standardization, it should be benchmarked and tested against a library of standard tests, and reproducible if you want to see some results. Max, how's the time, by the way? Am I on track, or?
Well, I think you're doing fine. It's
okay.
It's okay if we have slightly less conversation and more presentation. So, whatever you prefer.
Okay. Yeah, am I at about 10, 20 minutes right now? Or?
Yeah, basically, you're about 20 minutes in.
Okay, cool. Okay, so now we'll talk about the actual implementation of the software. And so, as the points that we mentioned earlier, extensibility, modularity. So we wanted to build it from the ground up, where what were the things that would be constantly reused in MCTS? So we thought about this. So we have a very, very base class, the solver, which consists of the green is an abstraction, which is not defined exactly, but the yellow is implemented. So calculating UCT, running the tree search, but how you do selection, expansion, simulation, backpropagation, these are not yet defined yet. And then moving forward, sorry. And then we have another one at the bottom. Sorry. And then we have 2 types of solvers that kind of inherit from the original solver. And these do define how you do the selection, expansion, simulation, backpropagation. I will get to that a bit later. But as you can see from this chart, it builds on top of each other. There's no like this is the code. No. If you want to create another solver that runs that does the key mechanisms a bit differently, you could, in principle, inherit the original solver and rewrite the other class. And that's what it means by extensibility here. And this is one of the innovations that we wanted to bring to the table. And then defining an MDP, we were talking about MDPs earlier. Defining the MDP is not defined actually. Let's say you're playing, one MDP obviously different from another MDP. It's completely separate from the solver. Again, the user defines this separately. and the two worlds will kind of meet at an interface. And so what do I mean by defining an MDP? Okay, so an MDP could be a deterministic one, it could be like a game, it could be Connect 4, it could be Reversey, it could be some, or it could be stochastic, like 2048 is a stochastic MDP actually. And so you define a 5 key abstract functions, which you have to define, how it transitions from state to state when you take an action, how the rewards are returned, the reward is always a double, the initial state that's in, when is that state terminal, so is the game over, and the available actions in each state. So this is how you define MDP, just 5 methods. You can define however you want. It can run a separate game engine, it could be internal to this, but you define this these 5 things. And our generic solvers will actually be able to then run Monte Carlo tree search. But if you want to also make your own Monte Carlo solver, you can by extending these classes. So there's a twofold here. So these are defined by abstract classes, and you have generic types. So state and actions are not, it could be double, it could be int, but they're generic types and that represent the state. It could be some custom thing that you defined. So it's very generic, very abstract, as the name suggests. But yes, this is how we would define MDP. So for example, you can write a Connect 4 game using just following these 5 principles. You could write a more complex MDP in the logistics world. You could write a simple game that you created, as long as it obeys these these abstract functions. And so, okay, so then in the bottom here, we define a solver. It's just probably better to have an actual full diagram as in the paper instead of in the half now. Okay, for later. So let's say here we have a solver and it's running simulate. And then we have different MDPs that we define. Here's 2048, here's Reversey. Yeah, it's very hard to see exactly from going. Okay, anyways. Yeah, so this is the game side where it actually runs a simulation and then runs and then solves for these games. And I think it's better to probably do a demo, but okay, yeah. Again, as mentioned earlier, the user is free to redefine the core functions of Monte Carlo tree search. So if you actually want to change the way selection is done, or change the order of expansion and simulation, you can actually do this. Some other MCTS algorithms work like this. It's very simple to do. You just basically switch the order of the simulation. I'm sure the simulation block here. You redefine this, and then you can change the order around. And you can change how you want to do MCTS. You want to add a heuristic. Okay, cool. You can go and maybe when you do the simulation or you do the expansion, you want it to be guided by domain heuristic. You can go into a certain block of code and add in that change by basically creating a new solver and redefining the expand class, for example. And so it makes it very easy to come up with hypothetical changes to MCTS and then add them in by extending the original solvers. And this is what it was designed for. Also, yeah, and the other thing I want to mention is that, so we can see here in the top, we have the solver and we have the MDP. They communicate with each other through an interface. And this interface is defined here, as I explained earlier. As it's simulating, it will constantly be querying this interface to get the data that it needs in order to do the tree traversal represented by this diagram. So speed is affected by how fast this interface works. So it's always better to make this interface performant. Okay. Again, I just talked about the key mechanism and how they can be defined. And another key thing. So as you notice here, we have 2 types of solvers. One's generic solver and one is stateful solver. What is the difference and why do we pick this? Well, going back to the diagram here, going on this tree search, we want to think about how we represent states as an agent goes down the tree. And do we need to explicitly keep track of it? And so now it's an area of optimization where, okay, we can develop one type of solver where the simulations don't actually have to explicitly remember the state, and a version where it actually has to explicitly remember the state. And now it's a classic trade-off between memory versus computation, right? So we decided to default to the stateless solver. Well, as you traverse the tree, the states aren't really remembered exactly, but in order to figure out where you are or approximate where you are, you replay the game. And so it's more memory efficient, but you have to compute more. And this is favored when the state action state branching is high. So what does state action state branching mean? It means that on average in your world or your MDP, for any state, any action you take from a state, how much branching are you going to on average get? If that branching is high, then you try to go with the stateless solver where it relies on computation to figure out where you are and not memory. But if you're in a world conversely where that state action state branching is low, so there's only a couple of states and each action you take is not going to land you another, it's not going to give you that much diversity of states, you might want to consider using the stateful solver where it relies on memory for you to remember where you are on the search tree. And so these are two flavors of solvers, and the user is even free to define even more types of solvers if they want to optimize further. But these are the two that are offered by default by the package. Cool. So now it's demo time. So I'm going to just quickly demo the workings of this technology. So we actually added in some Gradle tasks that will actually run the code, and we're going to run a quick game of Reversi here. Is everyone familiar with the game of Reversi, by the way?
I'm not. So maybe you can explain it.
Okay. All right. So I will explain. But it's basically the game looks like this. You can see where your board, where you place, let's say you're black and you place black here, it will basically, if you have two endpoints of the same color, it will turn the whatever's in between into that color. And the goal at the end of the game, when you have no possible moves left, to have as many of your color as possible. So now we've initiated a reverse UI, and it's actually running MC Tree Search for J to play the game. And so, so if no one's a reverse expert, I'm going to just have to play. I'm also not a reverse expert. I'm just going to demonstrate. So we'll start the AI. Okay, so I think the AI is the phone, and I am the star. And then the phone goes here, and I will go here, and I'll see I created my own blocks here, and it went here, and then I will go here, and then it also went here, and I'll go here, and then it went here. So I guess I'll just keep playing this game. I'll lose because this is a much better program than me. I'm not a reverse expert either, but just to demonstrate that, you know, it's under a novice, playing against a novice is pretty good. But of course it's not state of the art yet, because we haven't sort of, I'm just gonna play through this game real quickly. See, I'm playing through this game.
So could you make it
cool.
play?
It looks...
This is super cool. Could you make it play itself in theory? Like, can you?
Yeah,
can the interfaces match up?
That's actually what I'm gonna do next. I just wanted to finish this game real quickly to show you guys that
go for it.
It's an AI that actually works and it's not bullshit.
I think it's cool. I didn't think of what the strategy would be, but the AI trying to get the sides so that there's no way to get to the other side of it is nice.
Yeah. So I just played a game with our AI here, and as you can, I lost tremendously, but I'm not a reverse expert. But as you said, this is actually pretty fascinating because this is just basic MCTS. It is not any sort of primed up turbocharged version of it. It's basically just running what we talked about on the slides. It's basically just running. Sorry, I had a cold yesterday. Sorry, I had a cold last week and it's lingering on me. But it's basically running this, what you see here with this equation. There's nothing else it's vanilla, so to speak. There's no additional things it's running. And so it was able to tremendously destroy me in this game, but I'm also not a professed expert at this game at all. So now that Max just mentioned, can it in principle play by itself? And yes, so what if we want to, as I mentioned, improve on MCTS? We wanted to make it even better. So we can, and we will demonstrate this by simply adding a heuristic here. So here, we're gonna implement this heuristic here where now we give the MCTS a bit of domain knowledge. We want to, so again, if you get the corner, that's a key spot, that's like 100 value. And then closer to these sides here, that these are higher values. So it's domain knowledge and wants to explore that area more now. We want to tell the solver, I think it was at the selection or the expansion stage, I don't remember exactly. We want to tell one of these states to look for that more. And so we basically took this domain knowledge and we programmed it into MC tree set for J. And if I can show you the code block, and Jun will know this a bit better than me, but if we have a heuristic solver here. No, this is just a base solver. Oh, never mind. But you could in principle extend the solver, implement this, and that's exactly what we did. And we have it play against each other, the original Monte Carlo tree search versus the newer improved heuristic version augmented with this. And I can run it real quickly and you can see for yourself. The sim, I think, or is it reverse sim? I think it's the keyword. To look at the keyboard 1 second. Keyword is reverse the adversarial sim. Okay, so now it's going to play against each other. Just compile it a little bit. This is funny. Usually it's a bit faster in compilation, but so now it's running a battle between the heuristic augmented MCTS and the original base solver. And it'll just see, you see heuristics winning, the base is winning, but it'll run through the thing, and we actually demonstrate that. Go back to our paper. I'll let that run on the background, but we actually show that when we augment the MC tree search solver, we actually have a higher win rate of, this is the, yeah, we have to go 500 iterations here. We have 60% and 75% winning. So it has to have a more depth in the search because reverse is a much more complex game. If you increase the depth to 1,000, you'll have a better advantage. Heuristic augmented tree search with 500 iterations and 1,000 depth is going to win 75% of the time. So we demonstrated the effectiveness of adding a heuristic in there. And this example is still running on my machine, but you can see heuristics winning. Actually, they're kind of pretty even right now. Maybe we want to run more trials, but I have ran this much longer with more iterations, and you see that it's winning 3/4 of the time, which is a good sign. So now we demonstrate that we can potentially improve MCTS via this package by simply adding in a heuristic. And I can probably show you what a heuristic is added in. Maybe Jun can show you because it's on top. So here, okay, actually here, yeah. So we have this array for the heuristics, and we override the simulate function to incorporate the heuristics into the original simulate. So the solver has changed a little bit as a result of this, and it's playing against the original MCTS, and it's able to be better. So that's how you can improve MCTS, and this enables researchers essentially. If you have a research idea that you want to incorporate, then basically you can override certain parts of the MCTS algorithm and try it out for yourself. We also have a variety of other games that we support through MC Tree Search for J. We can play Connect 4 as well. We could play, we can do a simple game called Grid World. And what Grid World is basically, I can show you in the slides, is basically have an agent, and each block here is a state, and you can take up to 4 actions at each state. Here you can take all 4, up, down, left, right, for example. And ideally you want to get to the 5, but you can also end up in traps and hit -1. Everything else is 0. But the key takeaway is that if you choose to go forward, you only have like an 80% chance or X% chance of going forward. You could actually end up going to, it's not guaranteed that you go forward with each action that you take, with each direction that you take, right? So then this will basically just quickly solve, how fast. So the 2 optimal actions are left and down, and definitely not up or right. So basically, MCTS should be able to find out that these 2 are the optimal actions and solve it fast, and converge to the accurate results. And we see that it is converging to accurate results. The exploration term is going to be lower for the correct solutions, and the rewards are going to be higher for the correct solutions, and the number of visits to those states would also be higher. And so this just a quick sanity check on it is producing legitimate results when you're running on a basic example such as Grid World. And we just finished the simulation between heuristic and base solver. I don't know how many times base. Okay, so it was slightly better than the non-augmented MCTS. But of course, when you run even more,
just to kind of add a little bit to it, it also depends on several hyperparameters that you have set in the essentially for the simulation. Like how many simulations are you running per essentially MCTS iteration, and when you run the simulation, how deep can the simulation run for? Like how many simulation iterations do you run? So essentially, this also requires some hyperparameter tuning. I'm not sure what hyperparameters here are set to, but essentially in the paper results
I presented the paper
showed, we actually had a specific setting that actually demonstrate, oh yeah, it's better. Because for bad settings, you actually won't get any visible results.
Yeah, as you can see with 50 iterations with only 40 depth, it's basically the same, right? It's only for a complex game like Reversi, you'll need a lot more iterations and a lot more depth before you start seeing that, oh, the heuristic actually helps. Right. With just a pretty shallow search with a low number of iterations, 50 searches, like, okay, I mean, there's only so much you can find here with 50. Anyways,
and
okay,
another kind of conceptually why this works is that by the default solver doesn't know it doesn't have any specific domain knowledge. So when it tries to run the simulation in the MCTS, it is completely random. But a completely random game of Reversi, where people are just both players are making random moves, it doesn't actually get very close to how a real game actually is played, which is why you tend to get some bad results. And MCTS can essentially converge on, let's say, a local minimum or something like that. The reason why the heuristic sim works a little bit better is it tries to simulate what real players would do, which is prioritize the better moves. Obviously, it doesn't capture all of the strategies in Reversi, but it's a simple heuristic that can drastically improve the results of MCTS. Essentially, it gets you to converge more quickly and more optimally to a better solution.
Cool.
Sorry. And back to you, Larkin.
Sure, thank you. Yeah, cool. So I'll just wrap it up quickly. This basically takes us to the end of the presentation. in summary, what did we do? We created a Monte Carlo tree search package, and Monte Carlo tree search is used to solve MDPs, but also POMDPs or multi-arm bandits. They're all kind of the same family of stuff. And we created a package that's modular extensible. So it's not something that it's meant to be changed and adapted and reused for research and development. I didn't mention, but it's relatively lightweight. So you can see it runs on my computer. Well, this is an i7 processor with 16 gigs of RAM, but it ran on my older MacBook with less power, and it can be competitive as an AI. So in principle, it can run on your mobile devices as well. Doesn't require supercomputing to support. It's a relatively lightweight piece of software, and it's only about 1,500 lines. The core library is even less, I think. So it's not a bloated piece of code. And it's meant to be a research platform, but it also has you can also directly import. Let's say you created a MDB-based game on your phone. You can, in principle, program it onto your phone. So without major work. Just plug and play, so to speak. So what are the next steps that we want to take with this project? Well, as I mentioned earlier, we want to explore potentially changing these selection expansion simulation and the ways in which you would do it, because doing it in this way is just the basic way. If you read the literature, there's actually a lot of ways that people do MCTS in different ways. They can change the order of the key mechanism. They can change this equation here, for example. They can, as we showed you, add domain knowledge. You can do a combination of the three. So that's one thing. So just trying different ways and how you do MCTS, and this sets the springboard for you. You can do this now. You can change MCTS and bend it to your will, so to speak. You can also, what we didn't talk about is marry MCTS with different methods like dynamic programming, deep learning, so to speak, reinforcement learning. These things are unexplored, and if you have a JVM implementation of something that runs reinforcement learning or runs, I don't know, deep learning or some sort of another form of AI, you can marry the two together, and where you can use. So for example, I know how dynamic programming marries into MCTS. You would run dynamic programming, and then when it goes to a certain location that it's intractable, you run a Monte Carlo method in place of the dynamic programming solution. So these type of things do exist, and you could use deep learning to augment MCTS, or vice versa. You can use MCTS to augment dynamic programming or something like this. So these sort of marriages are very interesting to me, and I think it would be very good to see a research being done in it. And there's already a lot being done in it. And I cited a couple in this paper, in this presentation, but more will be even cooler. And lastly, it'd be interesting to see if someone actually has a reverse C game on their phone or something. They develop an app and they just want to port this in and support and use it to support their AI for their phone. And this is not a research thing. This is a pure industry thing. You might work at a startup and you want to have basic AI running. You don't want to spend 3 months writing it. Just term-based AI, just port it in. And this will be another interesting thing that we want to see happen. So that's where we leave off with MCTS 4J. We can enter the discussion phase now.
Well, Larkin, thank you so much. That was fantastic. Maybe I'll kick it off. I can see the obvious application to things that are clearly games, but like as an academic, I'm maybe more interested in things that are not clearly games. I've seen a number of papers in the last 5 years at Oakland Security and Privacy that use multi-arm bandits to formalize different types of problems, but I don't remember what specifically. So I guess I'm wondering, are you aware of any problems that lend themselves naturally to I forget the acronym to MBP to the formalism that you have here, which are maybe outside of what we'd obviously think of as games, whether they're in security or elsewhere.
If you go back to the MDPs, Markov decision process. So I like to use this as a generic term to describe a variety of stochastic processes. MDPs could be deterministic. So for example, if you imagine grid world, it's no longer, if you go down, it's guaranteed to go down. So now it's just like an A-star search. Just find it. There's no stochastic element involved. But then if you add in, okay, only 80% of the time it goes down. So now we have stochasticity, and that complicates things. And so, or you could have the MA a multi-arm bandit where you're never going to change states. You're never going to go anywhere. You just keep trying different options. You can also have the POMDP where let's say in grid world, you might have, oh, sure, what you see is not what you actually get. You have a probability of going down, but you also have a probability of seeing something else. So the observation is also kind of hindered. So this is another complication in your stochastic decision process. So I think maybe a more broad term is stochastic decision process. How do we make optimal decisions when there's layers of stochasticity involved? One with the action, state branching. So you take an action, you go somewhere else, but not guaranteed. The other one is when you observe something, it's not what you actually see. Yeah, Jacob, how do you answer?
So thank you for the presentation. This is super cool. And a couple things that really stick out to me is that usually when someone does a paper, it's like, oh, we came up with this interesting idea. Here's a little proof of concept or some pseudocode or something. And you guys are like, no, we're writing a platform that people can use. And we're also going to go out and talk to different clubs outside of our school about this. I think that feels very creative and like a very good strategy. And I'm curious how you guys decided to do your paper that way instead of just like going, coding up a solution that worked for you and moving on to the next paper, which a lot of people do.
That's it. That's a very good question. I'm gonna finish just answering my last question, which was regarding the. So what I wanted to say earlier was that using this abstract class definition here, you could define a multi-arm bandit, you could define a POMDP, you could define MDP, you could define any family of stochastic processes. It actually is not restricted to MDPs, and this presentation might be a little bit misleading to say that it's only MDP based, because you could, in principle, design a multi-arm bandit where, for example, transition is not defined, is defined, but it doesn't go anywhere. Maybe just the same state is returned, and this would be an MAB now. This is a multi-arm bandit. And could you define a POMDP? It will be a stretch because the POMDP has a different extra layer observation. So maybe not, but you could in principle define a multi-arm bandit and use this technology to solve multi-arm bandit problems. And if it's running properly, it would basically run this thing here. It would just basically run this. And so yeah, so it definitely is backwards compatible. And then you can use it to solve deterministic games. So like Connect 4 or Reverse C, these are not probabilistic. So in a transition, you wouldn't define any stochastic element in a transition. It would just go exactly to where you want to go. And then this is now a deterministic search, but of course it doesn't search through the entire state space. And you can use it for both. Okay, now to answer Jacob's question. So, which is a good point. Like you mentioned, it's why do we build an entire software platform for a research problem? Well, one of the criticisms I have against research these days is that a lot of research is not reproducible. The code is not very optimized sometimes. A lot of redundancies going on. And so we wanted to do something that had, as I mentioned in the first place, had dual purpose. One is you could use it as a platform to springboard research. Two, you could just use it as an application for your phone or a computer or whatever, for your application, and import it as a standard Maven package. So we wanted to have both bases covered, and this was the ambition of ours. And having this second base covered is not really rewarding on the research side, but something that we wanted to challenge ourselves and do. And the other reason is also we have a lot of industry experience going into graduate school. So we've done a lot of this stuff in our companies and respective companies, and we want to bring that expertise to the table. Why not make something fully end-to-end, fully importable in a Maven project, fully reproducible, and fully tested and traced, and bugs are traced and tested to a higher standard? If we can do it to a high standard, why not? And why not make this the normal and the new normal, maybe in the near future? And so yes, we did go end to end with. We actually had many iterations of this code through the course of a whole year, writing in a very crappy way, and then realizing we could have done it a lot better and lean out the code, revisioning it a lot more, and then creating the standard Maven release cycle for it, getting it onto the standard JVM release packages in there, even having a CI/CD through GitHub, will auto compile, auto release. So this is all available. And if you're just a pure software developer, you don't care about Monte Carlo tree search, but you want a turn-based AI that's going to work, just go and define your abstract class of what happens to your game, and then import the Maven package, and it will run. And we would love to see this happen. If anyone would like to try, maybe in another meetup, I can present this, and maybe some we'll try it out, because in principle it should work. So the alternative, as I mentioned, is to spend 3 months creating your own AI package that's not tested, that could be broken, that could be not performant, not extensible, or you can just import this and run it. And if with the universe of JVM programs out there, this is definitely a possibility. And it has the potential to do further research on. You can change it. You can extend this and change it and rewrite it and redefine it. We designed it in this way, and I really, and I'm hoping to get maybe some graduate students collaborating with this on this to extend it further. I know I will at least try to get people at my institution to move forward with something like this, but there are no guarantees. But we set that platform to say now it's easier for you to redefine Monte Carlo tree search the way you want to answer your research problems. Let's see if we can make this a new normal. Let's see if we can do research further. And I think we will see 1 or 2 new papers coming out maybe in 2022 that use this to do research on MCTS. Maybe I'll drive it forward. Maybe another person will drive it forward, and I'll be a support. But this would be a great thing to see. So yes, to answer your question, I went off on a tangent here. It's dual purpose. One, it can be industry used. If you just want to import it in and use it as standard, use it. 2, you can rebuild it and answer your research questions. It has two purposes at hand. And this is kind of a reflection of our experience too, right? We worked in industry for quite some time before going back to graduate school, so we built it in that way. Yeah.
I love it. I think that should be the new normal for a lot of grad school projects. Sorry for interrupting the previous question, and I appreciate the presentation. I've got to head out though, so
thank you
guys so much.
Thank you. Yeah, thank you so much.
So Jacob told me a while ago about how in the Windows operating system, there's like this marauding application that kind of looks for suspicious activity in a way that's troublesome if you are doing suspicious activity on the Windows operating system. And I guess like in general, I think OSs and even networks today have these types of things where you'll have some sort of process that kind of, for instance, if you have some large network, it like walks across the network and looks for anything that seems suspicious and reports it. And so I'm only have like a half-formed thought in my head, but I guess I'm wondering if there might be a way to treat these types of problems as a game, like an evasion game. A similar thing, we recently submitted a paper that had sort of an evasion game in a context where there were literally moving sentries looking for you, and you had to kind of navigate through them without them. They could see you, but they had to think that you were doing something innocent and not doing something not innocent. And so there were like things you were allowed to do, and your kind of evil strategy had to be close enough to a good strategy that the sentries couldn't figure out what you were doing. You could imagine like in a prison, you're trying to do a prison escape, but every part of the prison escape looks like you're doing something innocent, like going to the bathroom. So I don't know. Do you have any ideas about kind of concrete problems that would be tenable like this? Maybe the sort of sentry type things I'm imagining, or maybe something else, or am I maybe too far out there because these are like untenably large types of systems I'm describing?
No, I mean, whatever you claim, if it can be formulated as an MDP or something subclass of MDP, it can be in principle solved using this technology or Monte Carlo tree search in general. The only thing that I would say that may have a bit of problem is the POMDP, the partially observable MDP side, where what you see is not always what you get. what you are at. So you can't really observe the state very well. This is a classic problem of robotics where you can sense something, but then it's not exactly where you are. So maybe it might work in this framework. Yeah, it has to be modified for that to work. But if there's no problem of observation, if you observe something, you exactly what you get, then it will work. And usually for most like computational experiments, this is the case, especially where I work in, which is optimization and supply chain. But in robotics, this may not be the case sometimes when we have real sensors. So to answer your question, I didn't quite understand your explanation of the century problem very well, but if it can be formulated in an MDP, then in principle, you can run this type of technology on it. That's not an issue.
Yeah, I was sort of dodging around the exact formulation because we have something in review, but a similar problem to the one we discussed would be kind of, you have like a grid world prison and you want to escape the prison, and you have to do so in a way where every step of escaping, it looks as if you're doing something you're allowed to do, and you have a list of things you're allowed to do. And so in principle, that seems like you could solve it using an approach like this. I guess I know from experience that the type of system I'm interested in has an enormously complicated kind of logic to the opponent, and so that makes me wonder like what sort of slowdown you'd expect when kind of the game becomes very complicated because your opponent is very complicated.
So I mentioned briefly earlier that this technology is hindered by here. So when you define this abstract class, you could define it inside of the function and just have the logic all in this class. You can also have it communicate with something outside of the code to get the next state. And this communication time is going to slow down the program. And we've experienced this with certain games like Connect 4 and stuff, where Jun actually profiled the code and he saw that, this game still runs because Connect 4 is not that complex, for example. But if it was a very complicated logic system or some sort of Monte Carlo sampling within the transition, or some sort of complicated reward function where a huge computation needs to happen to get it, that will slow down a process. And so if that's the case, if it's a state space where the state action space is just huge and we just query it and we get it back in a microsecond, nanosecond or whatever, it's just big, but we can just get it right away. It wouldn't affect the speed of this program.
Right.
But if in the computation of any of these functions requires some sort of complexity or latency involved, then that's where you're going to see a degradation in performance. And that's where you have to be clever about how you write this code, and you have to do further optimization. So yes, this could be a potential downside to this type of technology, as the classic adage goes. With generalization comes performance issues. So yes, I think it depends. The answer depends on how much computation the agent or opponent agent needs to get to get these values here, such that they can run the Monte Carlo tree search. And if there is a bottleneck here, we have to be clever. We may have to be clever about how you implement this in order to get it run fast. So that would be another potential issue to be addressed. And that's where certain performant codes that are not very extensible, not very generalizable exist, but they exist for a reason. Because of because of things like this, where maybe the transition is very hard to compute, and we don't want to make it so extensible at this point. Now we want to make it very, very native to that one problem that we're solving, and make every single optimization we need to make for that. But only if it's justified, I would say. From my design perspective, and I think Jun would maybe be on the same boat as me since we designed this, is that let's start with a general solution before you go into the custom solution. Where it's now a very generalized solution for everything. And then when you discover that your MDP, for whatever reason, requires a complexity for a transition or the reward, for example, and you've exhausted the world of clever solutions that you can get around this to compute complex transitions or rewards, then perhaps do not go for a solution like this. Go for something that's very native to your problem. But then you have to spend a lot of time building a unique solver for that one problem, right? So that's that.
Yeah, that's exactly what's appealing about this. I spend a lot of time messing around with Z3 and different model checkers for kind of ad hoc solutions to different problems that maybe, emphasis on maybe, could be expressed in a more general way and solved with MDP, which is an interesting thing for you to think about.
Yes.
Anyway, Larkin, we should probably wrap up. Surprisingly,
you.
we're likely to actually have a large multiple of the number of people who attended watch it on YouTube, because that appears to happen with most of the talks. So I guess if people are watching this virtually after the fact and want to reach out to you, presumably that's perfectly fine. They can shoot you an email, right?
No worries. I think I left it at the very top here. So we already got to the end of the video. Then it is here.
Fantastic.
Both our emails. And yeah, cool. I apologize. Yeah, I didn't really plan this presentation very well. I kind of
Oh, that's all right. We're a little informal anyway, and you had a nice small forum today, so it's perfectly great. Well, Larkin, this was a lot of fun. Thank you so much for joining us, and June, thanks for coming along. And I'll let you know once this is posted online. And I think this is interesting work. So I'm glad you're able to virtually make it out.
Thank you very much. Thank you very much for having us.
Yeah. Thank you too. Any potential collaborators or questions about this project, or contributors, or just want to learn more, just shoot us an email. Yeah.
Sounds good. All right. Thanks, guys.
Cool.